The derivative can be used to find the largest and smallest values of a function, its maximum and minimum values. But before we discuss how these can be found using the derivative, let's define these terms. Let's say what we mean by maxima and minima, collectively called extreme values or extrema. We say that a function f has a local maximum, capital M, at the point C if f of x is less than or equal to f of c, this value capital M, for x near c. So that means that there is an open interval around c from which, taking x as the input number, f of x will be always less than or equal to this value f of c. And similarly, we say that a local minimum is little m at the point d for this function if little m, that is the value f of the function f of d, is always less than or equal to f of x, with x being near d. Again, that means that if x is around from an open interval around d, then f of x will be greater than or equal to than this local minimum value f of d, that is little m. Now, if we let go of these conditions of x being near c or near d, and these inequalities hold true for all x, then we call these maximum and minimum values global. Another terminology, another word people use instead of local is relative, and instead of global is absolute. Now, let me show you an example. Here you can see the graph of a function in red. This is the graph of a rational function at the ratio of two polynomials. And as you can see, it has lowest and highest values, both locally and globally. So at this point, along the x-axis, it attains a local maximum, but this is not the highest, the largest value it can take. This is the largest value it can take, and so this is the global maximum for this function. And similarly for the minimum values. Now, let me remind ourselves of a nice property of continuous functions over closed intervals, the extreme value theorem, that says that if f is continuous on a closed and bounded interval ab, then it attains a maximum value and a minimum value at some points cd inside that interval ab, meaning that f of x will always be between f of d and f of c for every x taken from the closed interval ab. Now, this is enough for now. Let's answer some questions. Use the graph above to find the global maximum, capital M, and the global minimum, little m, of the function, whose graph you see, on the closed interval between -3 and 3. So pause the video and input your answers in the box. Hope you paused it and have inputted for the global maximum 1, that you can see the function attains at x equals 2, the global maximum value is 1, whereas the global minimum, little m, is -2, and this seems to be attained by the function at x equals -1, that's the global minimum. Let's look at the next question. Find the global maximum, capital F, capital M, of the function f of x equals 3 minus x squared. So pause the video and input your answer in the box. Hope you paused it and have inputted 3 for the global maximum, and that you can find by realizing that this function, 3 minus x squared, has x squared, a non-negative quantity, subtracted from 3. So if we want to give it an upper bound, it would be 3. It's never greater than 3, and indeed at x equals 0 it attains this global maximum, that is 3. Let's look at the next question. Find the global maximum, capital M, and the global minimum, little m, of the function f of x equals x cubed on the closed interval between -1 and 2. So pause the video and input your answers in the box. Hope you paused it and have inputted for the global maximum 8 and for the global minimum -1. You can find those by considering x cubed and realizing this is a strictly increasing function, and so it must attain its global minimum at the left end point of this interval, which is -1 cubed would be the value that is -1, whereas the largest value it will attain is at the right end point of this interval. So that's f of 2, which is 2 cubed, that is equal to 8. I hope you enjoyed this video, and I'll see you in the next one.